NASA's newest images of interstellar visitor 3I Atlas have sent the space world buzzing. From Earth-based observatories to cameras orbiting and even roving nearby worlds, the comet's strange look and motion have sparked one wild question. Are we just seeing ice and dust or something engineered? Tonight, we'll sift the facts from the frenzy, explore the evidence, and follow the mystery wherever it leads. For context, NASA classifies 3I Atlas as an interstellar comet captured in multiple official observations, while recent sky shots, including a Perseverance rover view, ignited online speculation. It's official. This isn't a local wanderer from our Oort cloud. The object we now call 3I Atlas is the third confirmed interstellar visitor ever seen cutting across our skies, its path unmistakably hyperbolic, the mathematical fingerprint of something that wasn't born here. Astronomers flagged its speed and open-ended trajectory from the first measurements. The numbers say it swooped in from deep space and will never loop back. That alone makes it historic, placing it in a tiny club with one Oumuamua and two Borisov, and explaining why every major observatory on Earth and around Mars has tried to get a look. The name tells a compact story. 3I means third interstellar, and Atlas credits the survey system that spotted it, the Asteroid Terrestrial Impact Last Alert System, with follow-ups consolidating the orbit until the interstellar verdict was in. Unlike a periodic comet on a tidy ellipse, 3I Atlas barrels through on a one-and-done arc, the sort of path you get when the eccentricity is greater than 1 and gravity can only bend, not bind. From a storytelling angle, it's the classic stranger rides into town scene. From a physics angle, it's a clean case of inbound, swing by the sun, and out again to the stars. News coverage has zeroed in on two threads: the science of a rare interstellar comet and the drama of a "did we just see a spacecraft" flare-up. On the science side, agencies are stressing that it's a comet, not a mystery craft. A dusty, outgassing body whose brightness comes from sunlight hitting a coma and tail. They've published the key milestones: discovery in early July 2025, interstellar status confirmed by its open trajectory, and a solar system tour that keeps it far from Earth. The broad strokes: no threat to our planet, perihelion, closest approach to the Sun, around late October 2025 near 1.4 astronomical units, and a distant pass by Earth later in the year. Those are the kind of concrete clock and ruler facts that cut through the online noise. Then came the Mars moment. As 3I Atlas swept past the red planet in early October, NASA's Perseverance rover pointed its navcam at the night sky and caught a stark streak, a single bright line against black, that ricocheted across social media. Some voices called it cylindrical, others whispered craft, and the comparison to Oumuamua's cigar rumours wrote itself. Engineers and astronomers countered with the boring and far more likely explanation. Long exposure image of a moving target can stretch a point of light into a bar, track the sky one way, and anything speeding through will smear. The rover's vantage point made the image irresistible, but the physics makes the interpretation straightforward. Reporters have also highlighted the logistics ballet around Mars. Orbiters and rovers coordinated with telescopes back on Earth to catch 3I Atlas from multiple angles during its close approach to the planet, close in astronomical terms, not a near miss. Speeds quoted in coverage are eye-watering, hundreds of thousands of kilometers per hour relative to Mars, but that's what you expect for an interstellar comet dropping through the Sun's gravity well. The real payoff of that geometry isn't a dramatic picture. It's the chance to measure how the coma evolves, whether the tail changes direction with solar wind, and whether tiny non-gravitational nudges from outgassing show up in the track. So far, the orbit behaves like a natural body with no sign of controlled maneuvers. If you're picturing a naked eye spectacle, temper expectations. Even at its best, 3I Atlas is faint, a telescope's only target for most observers. That's why the prettiest images you'll see online have stars turned into rainbow streaks while the comet looks crisp. The telescope was tracking the comet itself. Space-based views and big observatories have teased out a compact coma and a subtle tail, more dim ember than searchlight. The nucleus size is still an estimate with wide error bars, because the coma makes the core look brighter and bigger, but it sits in the small comet range, not the sci-fi mothership class. Another angle the headlines keep returning to is origin. Interstellar doesn't mean from nowhere, it means from elsewhere, and researchers have been running backward integrations to ask which galactic neighbourhoods could plausibly have ejected it. The leading narrative is that objects like this are byproducts of planet formation and long-ago gravitational scuffles, flung out of another star's nursery and left adrift until gravity gives them a brief cameo in someone else's sky. That's the deeper thrill here. This is a physical sample of another system's leftovers, a messenger bearing chemistry and behaviour shaped under a different sun. Is it a spacecraft? Sidebar refuses to die, partly because Oumuamua's odd-like curve primed audiences to suspect the weird. But the checklist for a real techno-signature is more demanding than a suggestive photo. You'd look for narrowband radio, engineered flashing patterns, heat where there shouldn't be heat, or course corrections inconsistent with outgassing. None of those have turned up in the monitoring notes so far. What has turned up is exactly what you'd hope for in a comet. Outgassing activity, a dust-rich coma, and a trajectory that fits a natural interstellar interloper. In other words, the mystery isn't who built it, but what can it teach us about places we've never been? For timeline keepers, the near-term beats are set. The late October swing by the Sun, continuing observations from Earth and spacecraft en route elsewhere, and a distant flypast of Earth well after that. The value of those dates isn't spectacle, it's consistency. Multiple wavelengths, multiple vantage points, one object. That's how a story like this moves from splashy headlines to hard knowledge. How big the nucleus really is, how volatile rich the ices are, and how interstellar comets weather their first sunlight in eons. That's the promise of 3i Atlas, a rare real visitor that lets us test ideas about worlds we can't yet reach. Start with the first frames, the quiet kind that almost nobody notices. A faint, slightly fuzzy point is sitting where the night before there was only darkness. Blink one image against the next and it jumps a fraction of an arc minute. That tiny hop is the giveaway. Discovery teams take rapid sequences, then either track the stars so the comet smears, or track the comet so the stars smear. If the stars are pinpoints and the visitor is a thin streak, you're looking at a sky locked to the cosmos while an interstellar object sprints through the frame. Flip the tracking, and the object turns into a compact glow while the stars drag out into long scratches. Either way, the motion is the message. This thing is not bound to our sun. Follow-up images sharpen the personality. Big mirrors and sensitive detectors start to tease out a condensed coma, a hazy envelope of gas and dust, plus the faintest suggestion of a tail. In stacked exposures, the coma looks roundish, sometimes with a subtle fan that changes from night to night as the viewing geometry shifts. Don't be fooled by the aesthetic. When telescopes track the comet, the stars become luminous brush strokes. When they track the stars, the comet turns into a dash. Both are true views. The difference is the choice the observer made before pressing the record. Now to the frame that lit up the internet, a single stark streak captured from the surface of Mars. Perseverance pointed its navcam into the night and caught a bright line cutting the sky, clean, crisp, and irresistibly cylindrical to the human eye. That one look birthed 1,000 captions, craft, probe, mothership. The more grounded explanation is simpler and frankly more interesting. A long exposure of a fast mover from a camera, not designed to track deep-ski targets, will stretch a point of light into a rod. Angel the trail against the sensor grid and you get a bar, a touch of saturation along the core, and you get a solid tube. Nothing about that shape requires engineering, only motion, time, and pixels. Newsrooms and feeds ran with the drama, but the measured voices kept returning to context. The object swept past Mars in early October at tens of kilometers per second, Far enough to be safe, close enough to be bright for a robot with a modest camera. Multiple spacecraft at Mars and telescopes back home coordinated to watch, trading a pretty postcard for geometry, different angles, different phase lighting, different winds whipping the tail. From that choreography you can learn what the coma is made of, how fast the dust flows, and whether tiny outgassing nudges show up as measurable kinks in the track. As of now, the trajectory behaves like a natural body on a hyperbolic fly-through, not a guided vehicle making course corrections. If you've seen side-by-side comparisons online, one image showing a tidy dot, another a sleek cigar, you're looking at exposure time, tracking choice, and signal processing making art out of physics. Long exposures inflate faint structure. Short exposures freeze it. Track the comet and you'll see the coma's true shape but lose the stars to slashes. Track the stars and you get positional precision on the background field while turning the comet into a dash whose length encodes the exposure time. Stack dozens of frames and you can summon whispers in the noise. A fan-shaped jet on the sunward side, a filament swept back by the solar wind, a kink where the dust grain sizes change. These aren't illusions, they are the comet's own breath, written onto the sensor. The cylinder look has other more mundane helpers. When a bright trail saturates, electrons can bleed into neighbouring pixels, an effect imaged as a thicker, flatter core. Compression can add ringing and sharpen edges that weren't there. Slight jitter can segment a smooth line into a stepped baton. And if the camera's point spread function is a little asymmetric, the whole trail takes on a stylized, machined vibe. Add a dash of enhancement, contrast cranked, blacks crushed, and a natural smear becomes the kind of object our pattern-hungry brains label engineered. That's why mission teams keep pointing audiences back to raw frames and metadata before the aesthetic edits. Ground-based shots tell a complementary story. When observers lock onto the comet's non-sidereal motion, starfields elongate into neon rails while the nucleus region looks surprisingly tight. Zoom in and you'll often notice the coma isn't perfectly round. It has a sunward cusp and a tail that thins into the background. Under excellent conditions, hints of jets appear, narrow, brighter ridges, where sunlight boils volatiles from active vents. Those jets can make single frames look like elongated metallic bars if the exposure is just long enough to line up emission with motion. Give it another night and the geometry changes, the fan pivots, the brightness profile softens, and the bar becomes a puff again. That variability is the signature of ice and dust, not rivets and panels. Coverage has also leaned into the size guessing game, because images feel like they should tell you how big the nucleus is. In reality, most pretty pictures are dominated by the coma. The rock and ice core hides inside a luminous halo. Space-based data and high-end photometry put the nucleus in a modest range. Small by planetary standards, not the city killer some thumbnails imply, and the object remains comfortably distant from Earth even at its photogenic peaks. That's why scientists keep repeating 2 points amid the headlines. It's faint for the naked eye and it's never coming close to us. The spectacle is in the measurements, not in a sky-filling sword. From Mars, the lighting is different. The phase angle, the sun-object camera geometry, can turn a ghostly, diffuse puff into a sharper, higher contrast streak. Dust in the Martian atmosphere, the camera's pixel scale, and the absence of Earth-style light pollution all shape the aesthetic. A rover that isn't continuously tracking the comet will capture a clean, straight trail, precisely because the object races across its fixed field. That's the image we all saw, the trail of a natural traveller, not a portrait of its body. The body itself, unresolved at that distance and pixel scale, is simply too small for the camera to sculpt. So what should you look for when the next mystery bar drops into your feed? First, check whether the stars are points or streaks. That tells you the tracking choice. Second, hunt for the exposure time. Longer exposures make longer bars for fast movers. Third, compare the trail's direction with predicted ephemerides. If it lines up, you're likely seeing the comet's motion, not a camera quirk. Finally, beware of overly sharpened or contrast-crushed edits, that turns soft physics into hard edges. In this case, the more images you see, from Earth telescopes, from Mars orbiters and rovers, from space observatories, the more the story converges, a natural interstellar comet, imaged in every way our cameras allow, occasionally wearing a spacecraft costume, because motion plus time can make even a snowball look like a spindle. If you stare at a comet for long enough, it will try on costumes. In one exposure it's a fluffy seed head. In the next it's a machined baton. Give it 30 minutes and it becomes a glowing spear. None of that requires an alien blueprint. It's simply what happens when sunlight, ice, dust, and optics collide with our expectations. Start with the actor itself. A comet doesn't shine like a rock, it breathes. Sunlight warms volatile ices, jets switch on and off, and a coma, the thin atmosphere around the nucleus, billows outward. Those jets aren't symmetrical. One active vent can push more dust sunward. Another can flare as the object rotates. And the whole plume can get combed by the solar wind. Freeze that mess in a single image, and your brain, tuned to notice edges and cylinders, sketches a hull. But it's a living plume, not plates and panels. Now put that breathing object in front of a camera. If the telescope tracks the stars, the comet sweeps across the detector and turns into a line. If the telescope tracks the comet, the stars turn into lines. Either way, you'll see straight, hard-edged shapes somewhere in the frame, because that's how motion integrates on a sensor. Distance travelled during the exposure becomes length on the image. The longer the exposure and the faster the target, the more the line looks like a rod. Add saturation and the rod fills in, becoming a solid bar that our pattern-hungry minds mistake for a fuselage. Even when everything is perfect, optics impose a signature. The point spread function, the fingerprint of how a point of light is smeared by lenses, mirrors, and atmosphere, is never a clean dot. A slightly astigmatic system makes stars into tiny ovals, and a fast-moving comet stretches that oval into a stylized baton. Charge blooming in CCDS, where saturated pixels leak into neighbors, fattens bright trails. Rolling shutter readout in some CMOS, sensors can tilt them. Debayering and sharpening can carve crisp edges that feel engineered. JPEG compression can add faint halos, turning a soft plume into something with ribs. None of this needs intelligence, just electrons, readout clocks, and software making choices. Atmosphere paints too. High altitude turbulence smears light differently from frame to frame, so a stack of images aligned on the comet will sharpen the coma but smear stars into pastel rails. A line on the stars and the comet becomes the rail. Differential refraction at low altitudes splits the colour slightly, so bright trails grow thin blue or red fringes, instant metallic sheen. Dust in the air on Earth or Mars adds forward scattering. When the sun object camera angle is right, the coma flares into a bright wedge that reads as a blade. Change the phase angle the next night and the blade pivots or vanishes. Then there's rotation. A small lumpy nucleus tumbling every few hours produces a light curve, brightening when a jet faces the sun, fading when it swings away. If you happen to take a long exposure when a jet is pointed just so, the coma's brightness profile elongates. Stack a handful of those frames and the jet carves a faint spine through the fuzz, the classic rod in a cloud look. Catch the comet a night later, and the vent geometry has shifted. The spine softens, conspiracy theories evaporate, and you're left with the same old snowball doing snowball things. The psychology is the final lens. Humans are superb at seeing intent in geometry. Straight line must be built. Right angle must be engineered. News coverage always gravitates to the striking frame, the one where the trail is solo against a dark sky, the one with just enough saturation to feel solid. Commentators riff on cylinders, craft-like silhouettes, and unnatural symmetry. Scientists counter with context, exposure time, tracking rate, plate scale, and the fact that a single unresolved point dragged across a sensor will masquerade as a bar. The two sides aren't even arguing about the same thing. One is reacting to an aesthetic, the other describing a measurement. there are reliable tells that separate crafty from craft. First, resolution. If the object is unresolved 1 or 2 pixels across before it moves, no camera can reveal shape. Everything you see is the trail of a point source, not the body. Second, consistency. If a cylinder appears in one frame but not in others taken minutes apart with different tracking, you're looking at integration, not structure. Third, physics across wavelengths. A real metallic artifact would reflect light like a bare surface and radiate heat like a warm rock. A coma-rich comet glows with gas and dust signatures and scatters sunlight with a colour slope that reddens gently. Fourth, dynamics. Natural bodies may show subtle non-gravitational acceleration from outgassing, but they don't make abrupt, fuel-costly course corrections that defy the fitted orbit. Headlines love the idea of powered motion. The orbit fits keep coming back quiet. Zoom in on the coma's own tricks. Jets emerging from shadowed caverns can be remarkably narrow at their bases, then broaden as particles spread out. In short exposures aligned on the comet, these look like luminous struts. When the nucleus rotates, the jet sweeps, a sprinkler effect, painting faint arcs across stacked data. If the processing emphasizes high frequencies to bring out detail, the arcs' edges get boosted and the brain stitches them into ribs on a hull. Flip the processing to suppress noise and the ribs dissolve back into mist. Same photons, different aesthetic. Even the background plays a part. A faint star intersecting the comet's path during the exposure adds a bright bead along the trail. Cue the window or porthole look. Hot pixels masquerade as rivets. Cosmic ray hits deposit sharp, short dashes that, if they land atop the comet's trail, create faux seams. Flat field imperfections imprint gentle gradients, so a straight smear can pick up shading that reads like paneling. If you're scanning thumbnails fast, all of this coalesces into a narrative your eyes write before your brain catches up. When the story moved from observatories to Mars, the theatrics got louder because the vantage point was so novel. A rover gazing into a pitch-black sky, a single brilliant bar across the image. No star clutter, no city glow. That aesthetic alone nudged people toward hardware. The technical reality is duller and more beautiful. A fixed camera, a bright moving point, and an exposure long enough to let the object etch its path. On Mars, the thin atmosphere and different dust load tweak contrast. The phase angle can amplify the sunward cusp, the result feels sharper. But feels is not is, so how do you read these images like a pro? Look for the metadata, exposure length, tracking mode, plate scale. If the stars are needles and the comet is a dot, the mount tracked the comet. If the comet is the needle, the mount tracked the stars. If the trail length matches the exposure time times the predicted sky rate, you're looking at motion, not morphology. If stacking is involved, ask whether it was aligned on the comet or the stars. Alignment defines what gets crisp. Compare frames from different nights. Does the supposed hull rotate with the object's day? Or does it pivot with the sun like a jet should? And if a single viral picture is doing all the narrative lifting, treat it like you'd treat a single eyewitness account. Interesting, but incomplete without the rest of the evidence. The news cycle has, predictably, orbited the spiciest elements. One unforgettable streak from a Martian sky became a Rorschach blot for cylinder theories. Think pieces contrasted that aesthetic with sober reminders that comet images are time integrations, not selfies. Commentators resurfaced memories of earlier interstellar visitors and their own optical illusions, using those episodes to argue for caution. Meanwhile, observatories kept releasing stacks where the comet looks exactly like a comet. Compact coma, faint tail, occasional jets, nothing that holds its craft shape across different techniques. Between the sizzle and the science sits the simple truth. Motion plus exposure turns points into bars, jets into spines, and snowballs into starships. The moment you account for that, the spaceship costume falls away, and a far stranger thing remains, ice and dust from another sun, behaving like physics says it should. Spectra are lie detectors. Point a prism, these days a space-grade spectrograph, at a fuzzy comet and the light splits into fingerprints. Bright emission bands from gases, broad bumps from warm dust, and a gentle colour slope from sunlight scattering off tiny grains. If it's just a rock or a machine gleaming in the sun, you don't get those gas fingerprints. With 3i Atlas, the moment astronomers pulled the light apart, the chemistry started talking. Early results showed a coma rich in carbon dioxide relative to water, unusually rich in fact, flagging this wanderer as chemically weird compared with many homegrown comets. That's the sort of thing you only nail down with a telescope that can see the key wavelengths where CO2 glows in the infrared. Why does CO2 matter so much? Water is the default comet propellant in sunlight. CO2 and CO tell you about colder, deeper layers and the environment where the comet formed. From Earth, CO2 is nearly invisible because our atmosphere blocks its signature at approximately 4.26 microns. But a space observatory can sniff it out cleanly. That's why the big headline in the data isn't just "it's a comet," but it's a comet whose breath is dominated by carbon dioxide. That implies 3i Atlas either assembled in a frigid zone beyond a distant star's CO2 frost line, or had its surface chemistry cooked and sorted by eons of radiation in interstellar space. Either way, the spectrum says natural ice and dust, not anodized alloy. Water is still in the story. Instruments reading the near-infrared bands around approximately 2.7 microns for H2O and the oxygen byproducts that follow photodissociation confirm the classic comet recipe. Water ice sublimating to feed the coma, with carbon dioxide pouring out in surprising quantities. Complementary measurements have also pointed to carbon monoxide, the more volatile cousin that lights up around approximately 4.7 microns. Here, the levels look closer to ordinary comet than outlier, which helps narrow down formation scenarios. Put simply, the gas mix is cometary, even if the proportions are extreme by solar system standards. At visible wavelengths, the chemistry plays a different tune. Classic comet emissions, Cn in the deep violet, C2, swan bands in the green, NH2, further redwood, ride atop reflected sunlight. If you see those bands at the right relative strengths, you're watching a soup of radicals born when sunlight breaks apart parent molecules in the coma. A spacecraft hull would not oblige you with Cn and C2 bands pulsing in time with outgassing. It would show a mostly featureless reflectance curve and sharp, specular glints, not a forest of gas lines and a soft dust continuum. The observations to date, folded together across telescopes, keep pointing to gassy snowball, not silent metal. Mid-infrared dust tells its own tale. Warm grains radiate with broad features near approximately 10 microns from silicates, the same family of minerals that make up much of the rocky stuff in our system. Catch those humps, and you learn grain sizes and crystallinity. You can even tease out whether the dust is more like fluffy soot or compact pebbles. Reports so far emphasize that 3i Atlas behaves like a dusty comet ramping up as it nears the sun. Brightness increasing, tail lengthening, coma texture changing night by night as fresh grains vent. The upshot for the spacecraft theory is awkward. Engineered surfaces don't shed silicate dust that flares in textbook thermal bands as they rotate. Comets do. If pictures can fool us, spectra are the lie detector. Point a spectrograph at 3i Atlas and the fluffy shape-shifting coma unravels into lines and bands that tell you what's actually there. In visible light, you look for classic comet neon signs, the violet C-N band near 388 nanometers, and the green swan bands of C2 around 516 nanometers. In the infrared, you chase the big drivers of activity, H2O near 2.7 micrometers, CO2 at 4.26 micrometers, and CO around 4.7 micrometers. Each one is a fingerprint. If this were a bare hunk of engineered alloy, you wouldn't see gas phase revibrational bands fanning out of a dust coma. you'd see specular sunlight thermal emission that tracks a solid surface and maybe narrow artificial lines. What observers actually found is the opposite: a gassy, dusty atmosphere wrapped around an icy nucleus, with the chemistry doing something wonderfully odd. The headline result came from the James Webb Space Telescope. Using its integral field spectrograph, observers mapped the coma and pulled out unambiguous detections of water, carbon monoxide, and, most strikingly, carbon dioxide. The surprise wasn't that CO2 was present, it was how much. The measured CO2 to H2O mixing ratio clocks in at about 8:1, one of the highest ever recorded in any comet, and far above the trend seen in typical long-period and Jupiter family comets at similar distances from the Sun. That single number flips the usual script about what's driving the outgassing. For 3I Atlas, CO2 is doing the heavy lifting. Why does that matter? In comet science, ratios are time machines. A CO2-rich coma can mean ices that formed or were stored where carbon dioxide freezes easily. Farther from a young star beyond a CO2-ice line, it can also mean the surface has been processed by radiation for eons, baking a crust that throttles water vapour while letting more volatile CO2 and CO leak out. Either way, the chemistry points to an origin story different from most comets we've studied up close in our own system. That's why coverage has leaned into the weird recipe angle. The numbers imply 3I Atlas remembers a colder kitchen or a harsher pantry than the one that stocked the Oort cloud. Webb wasn't alone. NASA's newly launched SphereX mission, an all-sky near-infrared mapper, joined in with early measurements, flagging an extended CO2 coma and backing the picture that carbon dioxide is widespread, not just a tiny jet. That's key because a localized plume could fool you. A global excess says bulk property, not a one-off vent. Taken together, the space-based results have nudged the conversation away from silhouette hunting and toward thermophysics. How heat soaks into an interstellar nucleus, how different ices light off with distance, and how a crust might gate what escapes. Meanwhile, ground-based spectrographs have been keeping score in the optical. In August campaigns, teams reported the onset of CN emission as the comet dipped inside approximately 3 astronomical units, but with ultra-weak or undetected C2, an unmistakable hint of carbon chain depletion, a known subclass where C2 runs scarce relative to CN. That's catnip for chemists and modelers because depleted comets often trace different birth environments or evolutionary paths. For 3I Atlas, the low C2 to CN ratio slots it among the most depleted on record, reinforcing the sense that we're sampling chemistry moulded far from home. Another eyebrow raiser. High dispersion spectra from large telescopes have picked up neutral nickel lines without corresponding iron, a quirky metal signature that has been seen in a few comets, but is still hard to explain since both elements are heavy and should be reluctant to vaporize far from the Sun. One proposed route is that metals ride out on unusual organometallic carriers or ultrafine grains that release atoms under mild heating. However it happens, the presence of gas-phase nickel alongside ordinary comet bands is yet another tick in the natural but peculiar column. Colour tells a quieter story. Spectrophotometry across the red and near-infrared shows a distinctly red spectral slope at shorter wavelengths that flattens longward of approximately 700 nanometers. That slope is textbook radiation-processed organic material, the kind of tholin-like gunk you build when ices and dust are bombarded for ages. It explains the dusky hue in images and meshes with the idea of a skin that insulates underlying water ice, letting CO2 dominate. The slope isn't a glossy metallic reflectance, it's the matte varnish of deep time. Put the pieces together and a coherent picture emerges. At larger heliocentric distances, 3I Atlas wore a mostly dust-driven CO2-boosted coma with weak or absent gas bands in the optical. As sunlight intensified, CN flickered on while C2 lagged, marking it as carbon chain depleted. Through it all, the infrared kept shouting CO2, with detections of water and CO present, but dynamically less important than usual for a comet at the same distance. If you were hoping chemistry might portray a machine, sharp laser-like lines, reflective alloys, or thermal behaviour inconsistent with ices, the data have been stubbornly mundane in the most interesting way. It's a snowball, just not the kind we're used to. This is why scientists keep contrasting the viral cylinder photos with the chemistry. New segments have focused on the CO2/H2O ratio being off the charts and on the depleted carbon chains, because those results are hard to square with an engineered origin, but easy to place in planetary disk physics. Where did the ices condense? How were they altered? And how does a crust mature in interstellar space? The chatter about alien tech makes noise, the spectra make music. As 3I Atlas swings through perihelion, observers expect water bands to strengthen and the coma's recipe to evolve in step with heat input. If the CO2 dominance persists unnaturally close to the Sun, that will sharpen the case for either an intrinsically CO2-rich build or an unusually effective insulating layer that keeps water locked down. Either way, the next weeks of spectra are the real enhance button. One more practical note for reading future updates. When you see numbers like AFR in the R band creeping upward, that's a photometric proxy for dust production. When you see QCN reported in molecules per second, that's a gas production rate. In late summer monitoring, AFR rose modestly while QCN remained at the low end for comets at similar distances, consistent with a coma where dust is plentiful but classic carbon chain gases are scarce. Keep an eye on the C2/CN ratio and CO2/H2O as the Sun turns the knob. Together they'll tell you whether 3I Atlas is just a cold-born cousin of our comets, or a bona fide outlier from a radically different nursery. Imagine the Martian night. Thin air, a horizon etched with cold basalt, and a rover staring up with a camera that was never meant to chase comets. Then, one clean streak slashes the black. That single line is what turned a routine observing plan into global conversation. It came during 3I Atlas's close pass by Mars, when geometry briefly made the red planet the best lookout point in the solar system. Closest approach landed around the start of October, with the visitor rushing past at roughly tens of kilometers per second and skimming by at a distance on the order of 29 million kilometers, close enough for skywatchers on Mars to try for a shot, far enough to be astrophotography rather than a near miss. From orbit, spacecraft teams queued up a choreography. The plan, publicly teased and discussed, had Mars Reconnaissance Orbiter readying its high-resolution eye, ESA's Mars Express and ExoMars Trace gas orbiter aiming to sniff and track, and ground controllers juggling narrow observation windows as the comet's apparent motion screamed across the sky. The attraction wasn't just a pretty picture. Different vantage points let scientists catch the coma under different phase angles, probe dust and gas variability, and compare Mars-based sightlines with Earth-based telescopes in the same hours. That long baseline triangulation is gold for measuring subtle non-gravitational nudges, from outgassing and for pinning down the coma's shape without confusing motion blur for structure. On the ground at Jezero, Perseverance's navcam became the unexpected star. 2 frames, black canvas, bright line, ignited the "what did we just see" storm. The rover wasn't tracking the comet, it simply held still as the object cut across the field, so the comet's unresolved point became a luminous rod proportional to exposure time and sky rate. The cylinder vibe? Pure kinematics written onto pixels. That hasn't stopped the buzz. The same frames have been circulated as cigar-shaped craft by excitable accounts, with calmer voices pointing out the exposure and motion explanation. Either way, those images anchored the Mars flyby in the public's mind. Real data captured from another world during a truly interstellar moment. There's a twist. Some analysts pointed out that not every mystery bar from that night was necessarily the comet. In a couple of circulated navcam snaps, the timing and path match Phobos, Mars's inner moon, darting through the frame, exactly the kind of thing that produces an elongated smear if you're not tracking it. That doesn't erase the comet detections, it just reminds everyone how easy it is to mislabel streaks in low-light shots and why teams emphasize raw frames plus metadata before declaring any single trail to be interstellar. If you were in the mission room, the goals for a pass like this would have been delightfully unglamorous. First, photometry from multiple sites to see whether the light's curve flickers on a rotation period as jets turn on and off. Second, narrowband or spectral measurements to test whether the strong carbon dioxide story that emerged earlier in the campaign still dominates near Mars's distance from the Sun. Third, astrometry, precise positions against background stars, from different worlds to tighten the orbit fit and look for tiny accelerations consistent with outgassing. It's that last piece that clips a lot of wild theorizing. The composite track still fits a natural gravity-dominated fly-through without the abrupt course changes you'd expect from a guided vehicle. Coverage in the last week leaned on that point. Active chemistry, yes. Powered maneuvers, no. You can sketch the camera geometry that made this window special. From Mars, the phase angle, the Sun-Comet camera triad, was large enough to backlight dust, boosting contrast. Against a star-poor Martian sky, a fast mover becomes a crisp trail rather than a dim fuzz. From Earth, by contrast, observers had richer star fields and bigger telescopes, but worse instantaneous geometry. Compare the two and you can separate processing artifacts from real structure. If the spine you think you see in a ground-based stack is truly there, the Mars frames at a similar time should hint at the same asymmetry once you account for the different angles. If it vanishes, you're probably looking at how stacking and tracking choices sculpted the coma's appearance. That's why teams were so eager to overlap Mars and Earth, observing runs over the same nights. Threads in the news latched onto the most cinematic elements, the cylinder, the mothership whispering, the hunt for a definitive close-up. But the more durable storyline has been about coordination. NASA's public materials listed a small armada of assets across the solar system planning to watch. Not just the 2 Mars rovers and MRO, but space telescopes and planetary missions stealing glances when possible. That breadth matters because the comet's breadth changes with sunlight and orientation. With multiple instruments, you can watch the coma evolve as Mars swings from one geometry to the next, and as the object heads for perihelion at the end of October. And about that chemistry, the Mars flyby doubled as a sanity check on the now famous CO2 dominance. Earlier infrared spectra from space showed an unusually high CO2 to H2O ratio, among the highest measured in any comet, plus CO and hints of other volatiles. If Mars-based vantage points caught the same pattern in a different thermal vol regime, it would strengthen the case that we're dealing with an intrinsically carbon dioxide-rich nucleus, or a crust that keeps water suppressed. That's why commentators kept pairing the dramatic streaks with quieter graphs. The light says snowball, not sheet metal, and the dynamics agree. For storytellers, the timeline practically writes itself. Discovery in early July, inbound ramp-up Mars on October 3rd to 4th, as the side stage where a rover could look up and catch history sliding by. Then the main event at the Sun near October 30th. The Red Planet cameo isn't just a teaser trailer, it's a calibration scene that lets the rest of the campaign lock in. Because Mars is far from Earth, any quirky processing tricks that haunt one dataset won't replicate in the other unless they're real physics. That redundancy is how you keep a viral frame from derailing serious analysis. Public debate hasn't hurt, it's actually been useful. Wild claims forced experts to explain frame by frame why a long exposure of an unresolved target will look like a rod, why a moon like Phobos can masquerade as a craft in a single still, why instruments prioritize signal over aesthetics when time is tight. The explainer pieces about why 3i Atlas looked so strange out of Mars were, in their own way, part of the science, walking through plate scale, exposure time, and tracking to show how you read a sky image like an engineer. That collective teach-in is the real legacy of the Mars moment. Millions of eyes learning how to separate drama from data in real time. Zoom all the way into the rover's perspective and you can feel the constraints. Navcams are optimized for terrain, not faint fuzzies. They ride a mast that vibrates if a wind gust hits. They swat cosmic rays and dust motes and still deliver clean frames. Against that backdrop, catching an interstellar object at all is a small miracle. A couple of seconds of exposure, a sky rate that turns a point into a dash, and suddenly a robot on another world has contributed to a once-per-generation comet watch. If you're hot to scripting the scene, hold the streak for a beat longer than feels comfortable, then widen out to a globe with 3 orbiters fanning their instruments, because that's what really happened. A planet and its machines looking up together as a traveller from another sun slipped by. Start with the numbers that don't care about hype. The orbit is open hyperbolic, which means 3i Atlas wasn't born here and won't be back. Fit that path to thousands of precise positional measurements and you get a clean fly-through, closest to the Sun around October the 30th, 2025, at roughly 1.4 astronomical units, then outbound past Earth's orbit at a safe 1.8 astronomical units in December. Those are anchor points, not opinions, and they're rare why mission briefings have kept repeating interstellar, distant, and no threat. Size is the next brick in the wall. The sharpest images so far, Hubble's, don't resolve the nucleus directly, but they fence it in. The upper limit sits near 3.5 miles, 5.6 kilometers, across. On the small end, it could be just a few hundred meters. Either way, it's a modest cometary core shrouded in a glow of dust and gas, not a rigid craft with edges and panels. That range tightened earlier, after more dramatic, ground-based guesses. The point of the Hubble work was to drag how big is the rock out of the realm of thumbnails and into data with error bars. Dynamics add their own kind of honesty test. Interstellar objects that vent strongly or unevenly can show tiny non-gravitational nudges as sunlight drives out gassing. That's what made people argue about Oumuamua. With 3i Atlas, orbit fits so far don't need dramatic extras. The track through the inner solar system is consistent with gravity doing the steering. Theoretical expectations even say that for a nucleus a kilometre or two across, the outgassing push should be minuscule, well below what early data could reliably detect. That's why sober updates have leaned on the phrase, flies like a natural body, even as commentators chase anomalies. Mars gave everyone a chance to check that claim from a different stage. The comet whipped past the red planet at about 310,000 kilometers per hour, 193,000 miles per hour, still 29 million kilometers away, close for science, not for safety. Spacecraft and rovers looked on, snapping images and gathering geometry that tightened the orbit and cross-checked any hints of weird acceleration. Coverage hammered 2 points at once. The streak in the Perseverance frames may look cylindrical, but the multi-asset campaign was about whether the path itself deviated from gravity. It didn't, within the precision of the measurements. All the while, the comet's appearance has behaved like comets do. Hubble and other instruments show a sunward plume, dust driven off the warm side, and the beginnings of a tail, both of which evolve with viewing angle and sunlight. That morphology matters for the "is it engineered?" questions, because a coma and tail are the natural consequences of ice's sublimating. Tanks and trusses don't make swan bands visible or a dust continuum in the infrared. The global look, fuzzy coma, variable fan, tail, keeps reconfirming the classification stamped on day one, active comet. Mass and density are harder. No one has weighed it on a scale, but you can triangulate. Take the size bounds, assume a comet-like density, and you get a body massive enough that normal outgassing can't yank it around much, especially at Mars distances. That's exactly what the time series astrometry implies, a gravitational trajectory that stays put as more positions pour in, with no abrupt course changes that would hint at thrust. When headlines flirted with anomalous acceleration, specialist voices pushed back that the claimed signals were, at best, on the edge of detectability or dependent on early noisy data. The working picture from teams fitting the orbit remains conservative. If you zoom from mechanics to chemistry, the evidence piles in the same direction. Spectra show gas, water, carbon monoxide and unusually strong carbon dioxide, plus warm dust. That cocktail is awkward for any artificial object narrative and completely expected for a sunlit snowball. It also explains why the brightness has crept up as 3I Atlas sinks deeper into the sun's heat. More sublimation, more dust, a thicker coma that hides the tiny core and makes it trickier to pin down rotation from light curves. Even so, groups have teased out a plausible spin period on the order of approximately 16 hours from careful photometry, exactly the kind of slow tumble you'd expect from an irregular cometary nucleus. Context keeps the claims honest. When news outlets breathlessly contrasted a cigar streak over Jezero crater with talk of alien probes, the parallel storyline from agencies kept returning to fit and physics, open orbit, safe distances, measured speed, Hubble-checked size bounds, and a coma that looks textbook. The Mars flyby hyped as the moment we might catch a shape turned into something more useful. Another vantage point to constrain the path and to confirm that a point source dragged across a detector makes a bar, not a blueprint. The weight here isn't a single spectacular frame, it's the accumulation of independent, boring measurements that all agree. Even origin talk, the romance of where it came from, folds back into the evidence. Studies tracing its speed and direction argue for a deep old provenance in the Milky Way's outskirts, not a recent ejection from a nearby craft-building civilization. That narrative aligns with the chemistry, a CO2-rich breath that hints at a cold birthplace or long surface processing in interstellar space. In other words, the object behaves like debris from a distant protoplanetary kitchen, not like something with a mission plan. If you put all of this on a scale, the orbit that calls for no secret engines, the Hubble size, bounds that fit a small icy core, the coma and tail that evolve with sunlight, the spectra that shout ice and dust, the Mars-era astrometry that stayed on script, the pan drops hard on the side of natural interstellar comet. The sensational counterclaims have made noise in the feed, but the quiet metrics keep stacking up the same way every time someone points a serious instrument at 3I Atlas. To figure out where this traveller began, you have to play the galaxy in reverse. Astronomers start with the orbit we can measure today, an open, hyperbolic path slicing through the inner solar system, and integrate it backward through space and time. That's tricky. Tiny errors balloon as you rewind millions of years, and the object has likely suffered countless nudges from passing stars and the Milky Way's gravitational tides. Still, a few anchors exist. It's coming to us from the general direction of Sagittarius, the crowded, dust-rich region of sky toward our galaxy's centre, which is why early explainers warned not to confuse arriving from the galactic centre direction with born in the galactic centre. The approach vector is a clue about the last leg of the trip, not a birth certificate. Velocity adds another breadcrumb. 3I Atlas is tearing through the inner solar system at roughly 130,000 miles per hour, about 210,000 kilometers per hour, a speed that practically advertises interstellar origin. Nothing bound to our sun shows up with that much excess energy. That speed also hints at age. The longer something wanders the galaxy, the more gravitational slingshots it accumulates from flybys with stars and giant molecular clouds, slowly ratcheting its peculiar velocity. It's no wonder commentators kept calling it a time capsule rather than a tourist. The most ambitious rewinds so far use precise stellar motions from Gaia to hunt for witnesses, nearby stars that 3I Atlas might have brushed past recently enough to leave a measurable fingerprint on its path. The researchers pushed the movie back several million years and identified dozens of close passages. None mattered. Even the strongest candidate perturber would have changed the comet's speed by a whisper, not a shove. The inference is stark. Whatever ejected this object from its home system didn't happen in our neighbourhood, and nothing we can identify locally explains its current beeline through the solar system. Kinematically, it behaves like a denizen of the thin disk, the galaxy's younger, star-forming component, even though its speed is on the high side for that population. That restraint hasn't stopped bolder origin sketches from making headlines. One modelling group argued that the object may have been launched from the borderlands, where the galaxy's thin disk overlaps its older, thicker sibling, a sort of frontier between generations of stars. In that picture, 3i Atlas could be unimaginably old, perhaps formed in a primordial planetary nursery, then tossed outwards and left adrift for billions of years before wandering into our sky. It's a romantic hypothesis with big uncertainties, but it maps neatly onto the public's intuition that such speed and strangeness must mean deep time. If you zoom in from the galactic map to the scale of a single star system, the physics of ejection is familiar. Protoplanetary disks spawn countless icy planetesimals. Giant planets scatter them like cue balls. In tight binary systems, the Kozai-Lidov effect can pump up eccentricities until small bodies are flung into interstellar space. In crowded birth clusters, close stellar flybys finish the job. Most of those refugees will be volatile rich, which is exactly what we're seeing here. Put differently, you don't need an exotic engine to explain an interstellar comet. You need ordinary planet formation plus gravity and time. Chemistry doubles as a compass. Webb's early spectra show a coma dominated by carbon dioxide, with water and carbon monoxide present but playing supporting roles. That recipe points to a cold birthplace beyond the CO2 ice line in some long-vanished protoplanetary disk, or to a surface that's been so thoroughly processed by radiation that water stays bottled up beneath an insulating crust while CO2 vents more freely. Either way, the ingredients sound like distant freezer, not metal shop, and they align with an ejection long ago rather than a recent local shove. The sky path we're seeing now also helps bound the story. From discovery in early July to the early October Mars side glance, the trajectory fit has stayed stubbornly simple. Gravity does the steering with no abrupt zigs that would betray thrust. That simplicity matters for origin work because every non-gravitational wiggle you'd have to model backward would smear the past even more. By staying boring dynamically, 3i Atlas lets the backtracing efforts treat it as a clean test particle in the galaxy's tide, a rare gift in a field where chaos usually wins. News updates leaned on that point as the Mars flyby came and went. Exciting images, yes, but the track itself remained textbook. Another small but telling clue is where the object will go next. After swinging just inside Mars's orbit at the end of October, it will arc outward and by March 2026, cruise past the realm of Jupiter on its way back to the dark. That outbound leg, combined with inbound speeds and approach direction, locks down the hyperbolic parameters that go into galactic rewind studies. In other words, even the calendar beats Mars in early October, perihelion near October 30th, Jupiter next spring, feed the origin hunt by tightening the present-day state vector. What about the suggestion, floated in some commentary, that 3i Atlas might be the oldest comet ever seen? That claim bundles several threads: the high speed, the failure to tie it to any recent nearby star, and the possibility that its chemistry reflects extreme surface processing. It's plausible in spirit and provocative in detail. Old in a galactic sense can mean many billions of years, but oldest is hard to certify without a smoking gun, and the best the data can do right now is outline a credible path. A planetesimal born far from its star, ejected by planets or a stellar companion, drifted for eons, and only recently sent skimming past our sun. The same restraint shows up in the technical literature, confident about interstellar origin, cautious about the exact cradle. All the while, the public conversation has ping-ponged between poetry and proof. One day it's the frontier of the early Milky Way, the next it's a sober explainer about how Gaia's star maps rule out any local birthplace. 1 hour it's a Martian sky streak framed as a craft. The next it's a reminder that the object's chemistry screams comet, and its dynamics whisper, "I've been wandering a very long time." In that chorus, the load-bearing notes are the same ones scientists keep returning to. Approach from Sagittarius. interstellar speed, a CO2-rich breath, and a path that, when played backward, points not to us, not to our neighbours, but to faraway kitchens where other suns once baked their own comets. Start with the real question, not the clicky one. What would it actually take for an interstellar visitor to cross the line from natural comet to engineered artifact? The checklist is brutally specific. You'd want repeatable instrument-confirmed signs of intent, powered course corrections not explainable by outgassing, narrow band or deliberately modulated transmissions, laser pulses, thermal hotspots or waste heat patterns inconsistent with ice and dust, structured light curves that look like rotating hardware rather than a lumpy nucleus, or surfaces that reflect like polished metal instead of a dusty coma. That's the standard engineers and SETI folks use when they talk about techno-signatures, and it's the Scale 3 I-Atlas has to be weighed on. No lower just because the images look dramatic. On dynamics, the data are stubbornly boring in the best way. When you fit thousands of precise positions, the comet's path through the inner solar system behaves like a clean gravity-only fly-through. Open, hyperbolic, inbound now. Outbound after perihelion around 30th October 2025 near approximately 1.4 astronomical units. That's the opposite of a guided vehicle executing thruster taps, and it's why mission briefs keep repeating no threat, no close Earth pass, and no detected maneuvers. The Mars side glance didn't change that. Simply tightened the orbit from a different vantage point. Spectroscopy, the chemistry test, keeps landing on Snowball, not Starship. Early JWST results show a coma dominated by carbon dioxide, with water and carbon monoxide present, plus dust and hints of other cometary species. That CO2/H2O ratio is among the highest ever measured for a comet, which is scientifically spicy, but it's still natural spice, a clue to a cold birthplace or a crust that lets CO2 vent more freely than water. An engineered shell wouldn't light up with comet gas emission bands at the right wavelengths. It would mostly reflect sunlight and radiate heat like a solid. 3I Atlas is doing the comet thing. Images are where imaginations ran wild. A Perseverance navcam frame from Jezero showed a bright line slashing the Martian sky, immediately branded cylindrical. The physics is prosaic. A long exposure of an unresolved, fast-moving point across a fixed camera will draw a bar, not a blueprint. Engineers flagged that instantly, and follow-up coverage emphasized exactly that. Motion plus exposure time, not a portrait of a hull. If you're hunting for intent, you don't read shape from a smear. You look for the kinds of signals above, maneuvers, transmissions, heat. None have turned up. Size arguments cut both ways in the discourse, so it helped when Hubble put proper bounds on the nucleus. The solid core is not resolved, even by Hubble, but the upper limit diameter lands around 5.6 kilometers, with a lower end a few hundred meters, well within the ordinary comet mass and moment of inertia regime, where sunlight-driven venting can explain subtle behaviour without any engines. Some commentators floated far larger values. The Hubble analysis is the sanity anchor scientists keep pointing back to. Because the word alien drags history along with it, people keep comparing this visitor to the first one. With Oumuamua, a small but statistically significant non-gravitational acceleration ignited years of debate about exotic ices versus radiation pressure versus sails. That was a special case that forced extra physics into the fit. Here, so far, 3I Atlas hasn't demanded that kind of exceptional explanation. The trajectory fits gravity within current uncertainties, and the spectra scream volatile ices. The lesson is not that engineered probes are impossible, it's that extraordinary claims need the sort of anomalies that persist after every mundane explanation is exhausted. So what would a real engineered signature look like on this object? Start with kinematics, abrupt or patterned course corrections that don't line up with solar heating, rotation phase or jet geometry. Then radio, a narrow band carrier at non-natural drift rates, or a repeating modulation that survives multi-telescope checks. Then optical, nanosecond scale laser pulses, the kind current searches can flag, or specular glints repeating with machine-like regularity. Then thermal, localized mid-infrared excess that rotates like a radiator panel, not a sun-warmed patch of dust. Those are all things our community already knows how to test for when targets get interesting. If any showed up, the tone of this conversation would change overnight. What we actually have from the sober side of the news cycle is a constellation of natural clues that also explain the online mysteries. The cylinder over Mars, exposure time art, not structure, the rising brightness and activity, standard sublimation as heliocentric distance falls, the chemistry weirdness, a CO2-rich recipe likely pointing to where and how the nucleus formed, not to machinery. The global message from agencies and observatories has been consistent. Watch closely, measure everything, but don't mistake a time-integrated streak for a spacecraft. Even that if it were a probe, why no signal? The question has a technical answer. We don't assume silence equals natural. We assume silence means no detection yet at the sensitivity and time sampled. Listening is ongoing in other contexts and our instrumentation is good, but there's been no public report of any narrow band or laser emission associated with 3I Atlas. Meanwhile, the things we have measured, CO2-rich spectra, dust continuum, gravity-only trajectory, already explain the observations that kicked off the speculation. There's also a Bayesian angle buried under the headlines. Our prior for icy debris from other stars is now non-zero and growing. Oumuamua and Borisov proved that, and our prior for stealthed probes happening to streak past and reveal themselves via perfect single-frame silhouettes is low. That doesn't shut the door, it sets the bar. And that bar is high. Repeating signals, resolved structures that persist across instruments and geometries, dynamics that defy sunlight and rockets without invoking ad hoc physics. Until then, the most exciting story is still the natural one, a messenger from another planetary nursery, coughing out unexpected CO2 and reminding us that alien chemistry doesn't have to mean alien technology. If you're guiding viewers on what to watch next, make it concrete. Perihelion at the end of October, spectra should get louder. If water bands explode, the CO2 dominance might shift. Continue cross-checks from Mars-side and Earth-side assets on the outbound leg, and any coordinated radio/optical listening windows that get announced. The signatures that would flip the narrative are specific and hard to fake. So far, the comet is not producing them. Only the physics of ice, dust, sunlight and motion written across a handful of beautiful, misleading streaks. Start with how a rumour is born. A single dramatic frame ricochets across feeds stripped of context. A bright bar slices through the Martian night. Captions christen it a cylinder. Threads avalanche. But the instrument never lies about what it did. In the Perseverance raw image archive, you can see the exact sol and local time, the specific camera, right navcam, and the unprocessed frame NASA posted, the same one users voted into the rover's image of the week. From there, geometry and settings do the talking. A fixed camera, a fast mover night sky, a time-integrated smear. That's not a hull. It's motion written onto pixels. If you want to play referee between internet hot takes and instrument facts, use a 3-step check. First, pull the ephemeris. Where was 3I Atlas on that date and what was its sky rate and position angle from Mars? Public ephemerides and even hobbyist tools tied to JPL horizons list those numbers, including the trail's predicted position angle, so you can see whether the streak's direction matches the comet's motion at that moment. Second, measure the streak length in pixels and multiply by the camera's plate scale to turn it into an angle on the sky. Compare that to the predicted rate times the exposure duration. Third, sanity check the plate scale from the instrument paper. For Perseverance's navcams, that's approximately 0.33 milliradian per pixel, so a fast target naturally etches a rod for multi-second or stacked exposures. If those three agree, you just falsified the cylinder claim using math and metadata. not the vibes. This is where newsrooms and niche blogs have split. The measured coverage has hammered the basics. Closest approach to Mars near 29 million kilometers at nearly 310,000 kilometers per hour. Perihelion around October the 30 at approximately 1.4 astronomical units, and a distant Earth pass in December, plus a notable Hubble constraint that keeps the nucleus small. Those are numbers you can verify on agency pages and wire reports. The more breathless write-ups, meanwhile, have leaned on the aesthetics. Cigar, craft, mothership. The antidote is to put the headlines beside the data products. NASA's Comet page, the Mars Raw Images Index and Hubble's size estimate force the narrative back to physics. Case in point, size. A few outlets have tossed around tens of kilometers, as if it were settled. The Hubble analysis actually sets an upper limit of approximately 5.6 kilometers for the nucleus, and it could be far smaller. That's the kind of discrepancy you can resolve in one tab, by checking the primary press materials instead of amplifier sites. When the instrument can't resolve the core, you don't get to infer a skyscraper-length craft, you get a bound with error bars. Hype follows the biggest number, the instrument gives you the tightest. On the chemistry front, the internet loves the phrase weird composition, and here the instruments deliver something genuinely interesting. A JWST spectrum with a CO2-dominated coma and a CO2/H2O ratio around 8:1, among the highest recorded for any comet. That's a marvellous natural oddity you can read straight from the preprint and agency notes, and it neatly explains the brightness behaviour as the comet moves sunward. It doesn't whisper engineered. It points to a cold birthplace or a crust that throttles water. When a post tells you aliens, put its claim next to the spectrum. Lines don't lie. Another internet trap is treating a single dramatic frame as morphology instead of kinematics. The fix is to triangulate. Space.com's explainer on the Perseverance image walks through why a fast, unresolved point becomes a line. A P's brief sets the Mars geometry. The Raw Images page timestamps the exact shot. Together they form a reproducible chain. Ephemeris arrow instrument settings arrow. Expected smear arrow observed streak. When the chain closes, the craft silhouette dissolves into a trail whose length and direction were forecast before anyone posted it. If you want to audit future claims in real time, here's a workable playbook for non-experts that mirrors what the pros are doing. Grab the ephemeris for the observer location, Earth or Mars, and note the on-sky rate and position angle. Tools like Van Bietenen's Tracker or the Sky Live are fine for quick looks. Pull the raw frame and its metadata from the hosting mission's archive. Note the instrument's plate scale from a peer-reviewed or conference paper. Compute the expected trail length. Rate, arc seconds per second, times exposure, seconds, convert to pixels with the plate scale. If the numbers match and the PA lines up, you're looking at a comet trail. If they don't, you've learnt something about either the image, stacking, tracking choice, or the claim, it's not the comet. 5 minutes, 3 tabs, no drama. The same discipline applies to expert hot takes. Commentary pieces have argued over whether the streak reflects stacking and whether the navcam's resolution could possibly resolve shape. You can check both claims. The navcam plate scale and documented max exposure tell you how much smear a single frame can produce. Hubble's non-resolution of the nucleus shows why a rover camera can't conjure a hull where even a space telescope sees only coma. When the internet elevates an opinion because it's spicy, instruments force you back to the constraints. Finally, resist the urge to let any one platform be your truth. For this visitor, the most reliable thread has been the chorus of independent, boring sources that agree with one another. The MPC circulars that formalise the interstellar designation, NASA's page laying out dates and distances, Hubble's upper limit, JWST's CO2-rich coma, and the Mars raw frames with timestamps. When those line up, the internet's most cinematic frames become what they actually are: artifacts of motion, exposure and geometry, beautiful, misleading, and, with a little homework, completely legible. Here's the road ahead, beat by beat, with dates you can circle. Right now, the geometry is sliding toward the moment of maximum heat, perihelion at the end of October. The official timeline has 3i Atlas skimming just inside Mars's orbit around October the 29th to 30th, 2025, at about 1.4 astronomical units from the Sun. Fast, bright, for instruments, and busy. That's the scientific big stage, when volatiles roar and tails reshape quickly. Agencies have repeated 2 anchor points alongside that date. There's no Earth risk, and after the solar encounter, it cruises past us at a very comfortable distance. From Earth, there's a short, frustrating window where the Sun blocks the show. The comet is near solar conjunction for late October, so most ground telescopes have to sit tight. The plan picks up again once it slides out of the glare. Expect a reappearance for Earth-based observing in early December. When elongation improves and the morning sky gives amateurs and pros a fresh shot at photometry and narrowband imaging. That cadence, brief invisibility, then a dawn return has been emphasised in public guidance, so the community already has slots penciled in for renewed tracking. The next few weeks are a laboratory for chemistry and physics. Teams will watch whether water's spectral lines surge as sunlight digs deeper, or whether carbon dioxide keeps dominating even as heat ramps up. If H2O bands strengthen on schedule, that supports the insulating crust picture. If CO2 stays king at these distances, it argues for an intrinsically cold-borne mix. JWST has already delivered a first epoch detection of an unusually CO2-rich coma. Follow-up near and after perihelion will check how the CO2/H2O ratio evolves with geometry and heating. Hubble, meanwhile, will keep snapping the changing dust shell and tail for context on jets, fans, and any outbursts. On the is anything weird happening to the path front, the watchword is acceleration. As more astrometry rolls in from multiple vantage points, orbit fitters will keep testing for non-gravitational tugs from asymmetric outgassing. The Mars flyby tightened the trajectory, and nothing dynamical has demanded exotic explanation so far. Perihelion is when subtle pushes are easiest to spot. If fits remain clean after that, it will further undercut claims that the object is manoeuvring. Public-facing updates have set expectations the same way. Gorgeous images are great, but the numbers should keep behaving. Spacecraft opportunism is the sleeper story. With the Red Planet cameo now behind us, attention swings to probes that might steal views from very different angles as 3i Atlas rounds the Sun. Coverage has specifically called out that Mars orbiters have been watching and that Jupiter missions may try for distant looks on the outbound leg. ESA's JUICE is a popular candidate mentioned by mission watchers. Even a handful of frames or spectra from a probe far from Earth adds precious geometry for tail physics and dust modelling. There's also a calendar of planetary non-events that still matter scientifically. After the late October solar swing, the comet passes well away from Venus in early November, then makes its far but handy Earth pass in mid-December, about 1.8 astronomical units, before a closer brush with Jupiter's neighbourhood in March 2026. None of these are flybys in the cinematic sense, but each is a chance to coordinate instruments that favour different wavelengths and phase angles. Having those dates nailed down lets teams schedule synchronised campaigns and keeps public expectations grounded. Expect a lot of before versus after plots. Photometry AFRO will be tracked night over night to see how dust production crests and fades around perihelion. Gas production rates for CN and FRIENDS will be cross-checked against the CO2-rich infrared story to see whether the optical carbon chain-depleted hints persist. Polarimetry runs will probe grain sizes and textures in the dust, while deep mid-IR looks chase the broad silicate hump near 10 micrometers for clues about composition and crystallinity. The news has already highlighted how unusual that CO2/H2O ratio appears. Watching those numbers migrate or stay stubborn will decide whether weird recipe is a transient surface effect or a stable fingerprint from a different planetary nursery. When it comes to images, brace for another round of illusions. As the comet brightens for instruments but hugs the sun in our sky, expect more streaks from fixed cameras and more star trail stacks from telescopes tracking the comet. The cylinder conversation will likely flare again as new long exposures drop. The answer will be the same one engineers and scientists gave this week. Check the tracking mode, exposure time, and predicted position angle. If the smear matches the math, you're seeing motion, not morphology. That meta lesson, how to read a frame, is now part of the public storyline. If a curveball is coming, it's fragmentation or an outburst. Interstellar visitors are thermal rookies. A sudden jet or a small shed fragment isn't impossible near peak heating. Hubble and the largest ground scopes will be on the lookout for duplicate condensations in the coma, asymmetric dust fans, or kinks in the tail that mark outburst timing. Should anything like that happen, orbit fitters will recheck for tiny accelerations, and spectroscopists will pounce to see whether the gas mix changes abruptly. Nothing in the data requires a breakup, but it's one of the few surprises that would genuinely rewrite the talking points. Once it clears the sun from Earth's line of sight, the object enters its goodbye tour. December gives Northern Hemisphere mornings a dim, telescopes-only target as it fades through Virgo and into Leo, still producing enough coma to keep dust and gas measurements going. The safe but useful December 19th Earth miss distance, about 1.8 astronomical units, lands squarely in that window, so expect coordinated sequences designed to stitch December light curves to pre-perihelion data without a gap. After that, attention drifts outward to the March 2026 Jupiter region pass, when solar wind and magnetospheric conditions could sculpt the ion tail in ways we rarely get to map from multiple platforms. Meanwhile, the public conversation will pivot from "what is it" to "what did it teach us?" Newsrooms have already settled on the beats. The Mars streak that looked like a cylinder but wasn't, the Hubble size cap that keeps the nucleus modest, the CO2 heavy breath that makes this visitor chemically intriguing, and the calendar milestones that mark a safe, distant exit. Each of the next checkpoints, perihelion spectra, December reappearance, and any opportunistic spacecraft snaps, slots neatly into that arc, turning a viral image into a long, testable story. Hold that last image in your mind, the Martian sky, the clean white streak, the breath you didn't realize you were holding. It's wild how a single frame can make us feel like we're standing on the edge of a revelation. But tonight, we didn't settle for a feeling. We walked through the noise and into the signal. We traded the thrill of a rumor for the deeper thrill of understanding. And somehow, that made the universe feel even bigger. 3i Atlas was never just a headline. It was an invitation to learn how cameras actually see, how spectra confess what pictures conceal, how gravity writes trajectories with a pen that does not care about our captions. We watched a snowball from another sun put on a spaceship costume for a few seconds of exposure time, and then watched the costume fall away under the light of better data. We saw CO2 sing louder than water, dust glow like warm embers, and a path through the inner solar system that bent, obediently, elegantly, exactly the way physics said it would. The story got better when it got truer, and still, the romance didn't vanish. It got refined. The real magic wasn't the idea that someone built it, it was that no one had to. Ordinary processes in alien places can produce extraordinary sights here. A planet-forming disk around a star you will never visit, a skirmish of gravity with a young giant planet, a long exile between suns, a chance encounter with ours. That's not less marvellous than a craft, it's more. It means the galaxy's most astonishing tricks aren't rare, they're routine. We just have to be patient and careful and curious enough to notice. So here's how we'll leave it. When an object like this shows up, listen to the instruments first. Look for the tells. Does the path demand a secret engine, or does gravity suffice? Do the spectra speak in the language of ices and dust, or in tones a machine would prefer? Are the shapes you're seeing actually shapes, or just motion traced onto silicon by time? Ask those questions and you become part of the investigation, not just a passenger on the hype train. It's not as flashy as shouting cylinder, until you realise you're holding a method that works on every mystery the sky throws at us. And yes, we'll keep watching. As the glow of perihelion fades and 3i Atlas drifts outward, new measurements will keep dribbling in, changes in dust production, tiny tweaks to the fit of its orbit, the way its chemistry evolves as it cools. Maybe there's a small outburst waiting out there. Maybe the CO2 story flips as sunlight digs deeper. Maybe nothing dramatic happens at all, and the most important line in the logbook remains. Behaved like a natural interstellar comet. That's still history. That's still the third time humans have had a front row seat to material from another star waltzing through our neighbourhood. If this episode did anything for you, made you double take at a streak, taught you how to read a trail length in pixels and turn it into a speed, nudged you to care about a humble emission line at 4.26 microns, then it did its job. Because this channel isn't here to smother wonder, it's here to aim it. To give you tools that travel, tools you can use when the next mothership clip goes viral, or when a late night press release drops a graph you don't think you can pass. You can, you just did. To the people behind the scenes, the survey team sweeping the sky, the orbit fitters chasing fractions of an arc second, the rover operators who dared to point a terrain camera at the stars, the engineers who turned raw photons into public archives, thank you. You handed the world not just answers, but ingredients. You let all of us cook. If you want to keep this investigation going, here's your mission after the credits. Drop your biggest question in the comments. What would convince you that something up there was engineered? A maneuver you can't reconcile? A radio tone that won't quit? A heat signature in the wrong place? Tell me. I'll bring your criteria into a future deep dive on real techno signatures, what they are, how we'd catch them, and where we're already looking. And if you know someone who sent you the cylinder screenshot and said, "Dude, aliens," send them this video, not to dunk on them, but to invite them in. Curiosity is a door. Let's leave it open. Before you go, take a second to tune your eyes. The next time a dramatic streak hits your feed, ask 3 quick questions. What was the tracking mode? What was the exposure time? And does the trail's direction match the predicted motion? If you can answer those, you're already doing astronomy. You're already separating the cosmos from the compression artifacts. We're going to keep following the messenger until it disappears into the dark. There's a kind of holiness in that. Watching a thing we can't keep, learning from a thing we can't hold. Somewhere, light years away, there's a star that once shared a sky with this little nucleus. Tonight, for a handful of weeks in the only lives we get, we share a sky with it too. That feels like enough. If this journey resonated with you, tap the like, subscribe for the next chapter, and ring the bell so you don't miss the post-perihelion lab notes. On screen you'll find our deep dives into interstellar visitors past, and a quick primer on reading spectra like a pro. However you leave with this. Wonder isn't the opposite of skepticism. It's the reward. Keep your curiosity calibrated, your enthusiasm testable, and your eyes on the night. I'll see you in the next one.